When looking at the enthalpy change in a chemical reaction, it is important to remember that this is an extensive property. So that means that if we increase the number of moles, we're going to increase our enthalpy of the reaction. So if we multiply a chemical reaction by a factor, we also multiply the enthalpy by the same factor. In our example, we are multiplying carbon plus oxygen giving carbon dioxide by a factor of 2. When we multiply the reaction by 2, we also multiply the enthalpy by 2. If we reverse the reaction, then the sign of our change in enthalpy is reversed as well, or made the opposite. So here, if we reverse it and have carbon dioxide breaking down into carbon and oxygen, our change in enthalpy is going to be positive instead of negative like it was before, because we flipped the reactants and the products. We also changed the sign of our enthalpies. And this kind of makes sense if we think about it, because if a reaction is giving off energy when it happens, then if we push the reaction in the other direction, it's actually going to require energy to happen. So if we take our carbon and oxygen to make carbon dioxide, but now we want to break that carbon dioxide up, we're going to have to put some energy into that reaction in order to make it occur. We can use something called Hess's law in order to calculate the enthalpy of a chemical reaction that is difficult to do. If it is made up of a series of steps of other chemical reactions, we can use their enthalpies to calculate the enthalpy of the reaction that is difficult. So in our example, we have A plus 2B giving us C, and then C breaks down to give 2D. Well, if we want to find the reaction of A plus 2B producing 2D, we can just add the enthalpies together because we added the chemical reactions together. So because this was an addition of reactions, it is an addition of the enthalpies. Our C will cancel because it's on opposite sides of the arrow to give us our new reaction, and we can calculate our new enthalpy. Some reactions are very difficult in order to calculate the enthalpy, and so this is the way that we need to go about finding it. Let's look at an example using Hess's law. We are given two chemical reactions with their enthalpies. We're given a third chemical reaction that we're trying to calculate the enthalpy for. So when I approach these problems, I look for something that is unique in the reaction that we're trying to make and in only one of the reactions we're given. So an example of this would be the P4. The P4 is only in that first chemical reaction. Now I look to see what is going to make them the same. So there is 1 mole of P4 on the reactant side for the reaction we're trying to make, and there is 1 mole of P4 on the reactant side for the reactions we're given. This tells me that I don't have to manipulate the reaction in any way. So I'm just going to write that first chemical reaction as it is, I'm leaving out the states just to make it a little bit cleaner and easier to follow. Because I didn't do anything to the reaction, I am not going to make any changes to the enthalpy. Now, when we go to the second reaction, or we're trying to make using the second reaction, chlorine would not be a good compound to choose because it is found in both chemical reactions, which makes it a little harder to identify what needs to be changed. But if we look, the PCl3 is only in the second reaction we're given and also in the reaction that we're trying to make. So I can see from the reaction we're trying to make, it is on the product side. The reaction we're given, it is on the reactant side. That means that we need to flip the chemical reaction. So I'm going to put the products on the reactant side and the reactants on the product side. If I flip the chemical reaction, that means I change the sign of the delta H. So it was negative, and now I make it positive. But this is not the only thing that we had to do. We didn't just have to flip the reaction. There is also a coefficient of 4 in the reaction we're trying to make, and no coefficient in the one that we're given. That means that we have to multiply the entire chemical reaction by 4. If we multiply the reaction, we have to multiply the delta H. Now, this is not an essential part of solving the problem, but I like to do it as a double check to make sure that I end up with the reaction that that we're supposed to. So the 4-PCl5 is on the reactant side, but it is also on the product side. So that means it is going to cancel. We have 10Cl2 on the reactant side and 4Cl2 on the product side. So in order to combine the like terms, that is going to result in 6 chlorine. Essentially, we're subtracting 4 chlorine from each side, very much like you would do algebra. So the result is P4 plus 6Cl2 is 4PCl3, which is exactly the reaction we're trying to make. For our delta H's, because we added the reactions, we are going to add our delta H's. Remember to multiply that second delta H by 4. In this case, for our new reaction, if I multiply by 4, I get positive 495.2 kilojoules. And so the delta H that we end up with is negative 1,278.8 kilojoules. So because it's negative, that tells us that it is an exothermic reaction. Here is an example for you to try. See if you can use Hess's law to calculate the delta H for this chemical reaction. When we look at our problem, we want to find something that is unique in that first chemical reaction. So copper is in both. We are not going to choose that as our compound. But if we look at our copper 2 chloride is only in that first chemical reaction because it is on the reactant side in the one we're trying to make, and the product side in the one that we are using, that tells me that we have to flip that first chemical reaction. Because we flipped the reaction, we change the delta H into a positive 206 kilojoules. We don't have to multiply by anything because the coefficient is the same for those copper chloride, 2-chloride. Now, if we look at the second chemical reaction, the thing that is unique is the copper 1-chloride. So because they are both on the product side and there's the same coefficient, we don't have to do anything to that chemical reaction. Because we don't do anything to the reaction, we don't have to change our delta H. We're going to add the reactions together. So the chlorides are going to cancel, or the chlorine gas is going to cancel. We have 1 copper on the product side and 2 on the reactant side, so one of those will cancel. And we'll get copper plus copper 2-chloride gives us 2 copper 1-chloride. To find the delta H, we add the delta H's together, and this is why the sign is so important. Our delta H is a positive 170 kilojoules. Because it's positive, that means this is an endothermic reaction. And we're going to have to put some energy into the reaction in order to make it occur.